In industrial applications, using automated systems is very common. And in order to control the behavior of these systems, you need some sort of controller. One of the systems can be, for example, an automated arm. And in order to control the movement from A to B of this robotic arm in a way that is quick and safe, you need a very robust controller. One of the most common controllers is the PID controller, and this is what we're going to talk about on this video. The objective of a controller is to be able to control a particular variable in a system in order for the system to achieve a desired state. A typical example of this is the cruise speed of a car, in which what we control is the acceleration and the desired state is a defined speed. So the PID controller is the most typically known controller and is composed by three elements: the proportional, the integral, and the derivative, which have different meanings that we will explain in a bit. So if you add all these three components, you will get the control signal. So for example, if you're moving a robot from one point to another point and you can control the acceleration, the sum of all these three elements will define the acceleration you need in order to move the robot from one point to the other. Another important thing is the error. The set point would be the desired position of this robot, and the process variable would be the current position of the robot. So the error would be the distance from the current position to the desired position. This is the error. So as I said, to get the new acceleration we need in order to move this robot, we need to add the proportional, integral, and derivative components. So what is the meaning of each one of these components? The proportional component is defined by the current error. So if the distance to the destination is very high, the proportional component will be very high. The integral is determined by the accumulation of this error. So if the accumulation of this error is high, the acceleration will be high. And the derivative component is determined by how fast the error changes in time. So the fastest the error is changing, the highest will be the derivative component. We can see here that each one of these components has a constant, Kp, Ki, and Kd. These are the constants that define how the PID controller is going to behave. And it's important to say that we need to tune these constants and define their values in order to get the best possible outcome for our system. So if we want to see this as a diagram, and you can find this diagram on Wikipedia, you can find the error, which is the difference between the set point and the process variable. With the error, you calculate the P, I, and D components, and with that, you define the control signal, which in the case of a robot will be the acceleration. With this new acceleration, you observe a new value of the system, which is how far you are from the destination, and this will be your y, which is the process variable, and so on. This is a feedback loop that is constantly updated in order to get new accelerations that are needed in order to achieve the final destination of the robot. So let's see how we do this in AnyLogic, in which we have this pallet rack and we move pallets from one position to the other using acceleration for this automated system in all directions. And to do that, we will use a mix of system dynamics and agent-based. So let's see how that works. Okay, so let's see what this model looks like. We have these different components that are important. The acceleration, which is the variable that we can control. We have the position, which is the current position of the system. The target position, which is what state we want to achieve. We have the error that we talked about. And we have the different components of the PID controller: the integrative, the derivative, and the proportional, which will define the control signal, which is U. The control signal is the same as the variable that you can control. So it's equal to the acceleration. But in general, in systems, you have a maximum acceleration that you can achieve. So this is why we use this function where we have the minimum acceleration, which is the maximum deceleration, and you have the maximum acceleration. So you will use the maximum or the minimum. If you're between this range, you will use U, which is the optimal control signal. So this is how you define the acceleration. The speed is the accumulation of the acceleration in time. So it is defined by this torque. And the position is the accumulation of the speed. So this is the speed, and the position is the accumulation of this speed. So it can be defined as a stock. This is the position of your robot. The error is the difference between the target and the current position. So this is what we call the set point, and this is what we call the process variable. So the difference between these two is the error. And with the error, you can calculate all the PID components. The proportional is simple. The Kp multiplied by the error. The integrative is the accumulation of Ki multiplied by the error, and this will give you the integrative component. And the derivative component is the differences between the errors divided by defined time multiplied by the constant. So in order to calculate the previous error, you can use a delay function with an initial state, which is 300. This is hard-coded here, but you should never hard-code. So you have the error that occurred this time ago. And this is just arbitrary. We define 0.01 seconds, but you can define anything that is according to what your system is. So we have the previous error and the error, and we can calculate the derivative, basically, which is the difference between the errors divided in time. So with these three things, we can calculate U, which is the new acceleration that we want to achieve, which is the proportional plus integrative plus derivative. This is the system dynamics model that you will need to use in order to use a PID controller. Now the question is, how do you define these constants? And this is what we call the tuning of the constants. And in order to do that, there are many techniques, and what we're going to use here is a parameter variation experiment. Now it's important to say that all the constants have units that you don't need to really think about because they are related to whatever variable you are trying to control. So for example, the proportional constant, if the error is defined in meters and the variable that you're trying to control is acceleration in meters per second square, it means that Kp will be 1/second squares automatically. You don't need to think about it. Okay, so let's talk about the parameter variation experiment that we do in order to find the constants that we want. Finding the constants might be really an optimization problem because you want to find the constants that minimize the time it takes for your robot to move from point A to point B. But in this case, just for simplification, we use a parameter variation experiment just to get a bunch of different results that we will choose from. So we can have all the parameters which are all the constants here that have a certain range that we choose arbitrarily, and we'll find, exporting to Excel here, all the values of the constants that give a very low time for the robot to move from one point to the other. Okay, so if we see the results of the simulation, you will notice that you have here, down here, all the Z movements from up and down, so the position to the left and acceleration and speed in the right. You can see that when this automated system arrives to the destination, it slows down very smoothly. This is not necessarily an optimal in terms of how fast this thing can go, but it depends on what kind of automated system you are representing. You can calculate this in a completely different way, and you don't need necessarily to use a PID controller. You can just calculate speed and acceleration manually, and that might work well, but it depends of what kind of automated system you are modeling. So this is it. There's a lot of information online about PID controllers if you want to learn more about it. And if you want to try a simulation to understand how it works, you can try to do something very simple on your own using the concepts you have learned on this video. So that's it. See you on the next one.